Greetings. My name is Mohammed. Urban flood modeling, a geospatial evaluation of building systems for resilient city planning in Lusaka at the 7th International Conference of Contemporary Affairs in Architecture and Urbanism, May 2024. The table of contents will include an introduction, literature review, study area and research methodology, results, discussion, conclusion, and recommendations, and references at the end. The introduction. As the human population and the impending magnitude of global climate change both continue to grow, there is an imperative to better understand the function of cities as ecosystems and their resilient to climate-driven disturbances. Floods are prominent disturbances to urban ecosystems. In Lusaka, city flooding has been aggravated due to rapid urbanization. Studies have also noted that variation in rainfall intensity and urban development in cities affects urban catchment through flooding problems. Now, according to ICCAUA, urban development activities that increase imperviousness, urban impact on the urban, which increases that risk. Urbanization should reduce while increasing and flooding volume. This internally in some urban areas. Now, what's an urban flood model? Researchers and environmental scientists use urban flood models as of and simulate water flow and other flooding processes, support risk assessment and immediate management in order to develop strategies to mitigate future flooding. Now, in this paper, we will define urban flood models as numerical models that are capable of representing the features of urban ecosystems and the mechanisms of flooding that impact them. Cities are social, ecological, technological systems, and urban flooding results from the dynamics of their social institutions, natural ecosystems, and infrastructure systems in response to meteorological drivers. Urban flood models must be able to represent all three social, ecological, and technological system components and their contributions to flood response. Our literature review involves a study done by Billy 2023, and it says that addressing the global challenge of climate change requires nations to develop advanced improved systems to mitigate its effects. However, in the case of Zambia, the current planning approach to the built environment has overlooked the impact of impervious surfaces and their contribution to waterlogging. The study area. Our study area was carried out in the suburb of Kamwala South, which is an area within Kawata constituency of the capital city. The constituency is one of 7 constituencies found in the greater Lusaka city, located in the southernmost part of the city. The constituency lies at an elevation of 1,280 meters above sea level, with a population of 228,000, according to the census and that was undertaken by the Zambia Statistics Agency. The constituency has no perennial rivers, but experiences floods frequently in the rain season. Now, our research methodology included obtaining meteorological information of rainfall patterns of the last 10 years from Zambia Meteorological Department, Lusaka City Airport Station. Now, land use information was gathered from the Ministry of Lands, while the digital elevation model was first obtained as a NASA shuttle to greater topography mission image footprint from the USGS Earth Explorer. The results. Among other factors that form the final map is a rapid flood assessment report, which was made available by the Disaster Management and Mitigation Unit. This showed proximity to streams, drains, and dams, and an elevation. While a map of basins was obtained after the watershed delineation process. The geographical landscape of Lusaka is predominantly flat, with a slight incline in the northeastern region, directing surface runoff towards the Kwerere area. Now, the majority of the city's elevation surpasses 1,240 meters, resulting in diminished flow of runoff and leading to the risk of floods in watershed cut zones, as shown in the final flood map on the next page. Now, what we have here is a map of drainage basins within Lusaka. The findings indicate that Lusaka is situated on relatively level terrain with elevations ranging between 1,155 to 1,342 meters above sea level. The final map shows flood-prone areas highlighted, where slope, variation, and other factors indicated a higher flood risk. Now, by using different shading to represent the level of risk of vulnerability, we're able to show how vulnerable these areas are. Lusaka's drains and streams were an obtained feature on the final map, and the residential area was shown as well. So as you can see, the highly shaded area are the most flood-prone areas, while the least shaded area is an area which is likely to be flooded during the rain season. So Lusaka has got many huge portions of areas that are indicated in this way, and this is the huge chunks of land. The discussion. The map of drainage systems was made after loading in flow accumulation, stream networks, and watershed maps. These parameters were used to mark points on water collection pathways, and it was understood that understanding the boundaries of a drainage basin is crucial for managing water flow and potential flood scenarios. Using our findings in slope, belt environment, rainfall runoff, and soil parameters, we showed that evaluating of flood vulnerability for different regions that seemed to coincide with the narrow pathways that were obtained using the drainage basins map from the delineation of watersheds were shared as flood vulnerable buffer zones and incorporated into the final map. The implications of urban flood management are that the findings of this study have provided valuable insights into the spatial distribution of flood risk and vulnerability within a city. This information can be used to prioritize flood management efforts, such as the maintenance and upgrading of drainage infrastructure in high-risk areas, the identification of critical infrastructure at risk of flooding based on the integrated analysis of social, economic, and hydrological data will enable proactive measures to protect essential services and minimize the disruption during flood events. Understanding the social, economic drivers of flood risk can inform targeted interventions to address underlying vulnerabilities, such as improving housing conditions in informal settlements or enhancing community resilience through capacity building initiatives. Now, the conclusion. significance of this project extends beyond the boundaries of the SAC. It provides a model for urban areas facing similar challenges, where effective drainage management is pivotal to public safety, economic stability, and sustainable development. By addressing the vital problems of urban flooding and presenting a multi-phased approach to solutions, this research not only enhances the quality of life for Lusaka residents, but also stands as a testament to the potential of proactive urban planning and the synergy between technology, science, and community well-being. It underscores the value of informed decision-making and the commitment to resilience in the face of environmental challenges. Now, the study's findings have a significant implication for urban flood management and resilient city planning in Lusaka. By addressing the strengths and limitations of the methodology and providing actionable recommendations, policymakers, urban planners, and stakeholders can work together to build a more resilient and sustainable future for Lusaka City. Our recommendations are that 1, it can strengthen community engagement and provide public awareness initiatives to foster a culture of resilience and empower residents to take proactive measures to mitigate flood risk. 2, the paper can integrate flood resilient considerations into urban planning policies and regulations, including land use zoning, building codes, and infrastructure design standards. 3, we can develop and implement targeted flood management strategies based on the study's finding, focusing on priority areas identified as high-risk zones. Amongst the notable limitations of this study include the data availability. Now, the data availability and quality may pose challenges, particularly in obtaining accurate socio-economic data and hydrological parameters at the required spatial and temporal solutions. Especially this is in a case for obtaining the digital elevation models for Lusaka, the digital terrain model, and all that. Secondly, the complexity of the modeling process may require specialized expertise and computational resources, which could limit the scalability and applicability of the methodology to other extents, to other contexts. Thirdly, the uncertainties associated with future climate projections and socio-economic trends may affect the reliability of long-term flood risk assessments and planning decisions. These were the references that were used in coming up with this presentation. I thank you very much for giving me the opportunity to present. My name is Mukamlenga. This is the end. Greetings.